All right, this week we're going to be talking about the electromagnetic spectrum. This is something that you're actually probably familiar with a lot of parts of this. It includes things like radio waves and X-rays and gamma rays and light and things like that. Waves, don't forget about the red slides. This is when you should take notes. You should have your waves handout. Don't forget to look for the owl and describe them at the end, and give me a 2 to 3 sentence summary of what you learned.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
All right, so the electromagnetic spectrum is the entire frequency range of electromagnetic waves, and you should know what that word frequency means at this point. But what exactly do we mean by electromagnetic waves? Well, you can see kind of the parts in that word. We can see part of the word electric there, and we can see the word magnetic in there. So electromagnetic waves actually have part of them that is electric, and part of it is magnetic. And they are organized from large to small wavelengths. The large wavelengths have less energy and the small wavelengths have more energy. This is a very important point because this gets into the idea of whether or not these types of waves are actually dangerous to us. So we have small waves over here at the gamma ray end, and then we go to X-rays, ultraviolet, visible light, infrared, microwave, and radio waves. Take a look at the picture at the top of your notes and you'll notice that it kind of shows you this there, that we have the wavelengths going up as you go to the left side here, and we have the energy going up as you go to the right side here, right? So long waves over here, right? Long waves over here, long waves, and really short waves over here, right? Short waves have higher energy. So, question, if this is the case, then which wave has more energy, red or blue? Well, take a look at these. Which wave is longer? We have the wavelength of this red wave here, these guys over here that are moving just to the right of that, and then we have this wavelength here of this blue light. So which one has more energy? Well, if you remember back what we were just talking about, shorter wavelengths have more energy. So that means that the blue actually has more energy because the wavelength is shorter. So if that's the case, is this correct? Well, I'm on a campaign to try to get this changed here. So the basic idea here is that blue is actually a hotter temperature than red because it has more energy and therefore more heat energy, more kinetic energy, whatever you want to call it. It's got more energy and so it is hotter. And so I think we need to switch these guys around and start making cold things, starting to label them red, and taking hot things and labeling them blue. And you might say, well, hey, isn't, stuff like ice and water and stuff like that, cold things, aren't they usually blue? Well, first of all, no, water's not blue, ice is not blue. It's clear for the most part. I guess it can be blue sometimes, but it's usually not blue. And you might say, well, isn't fire red? Well, if you look at a fire, it's actually several different colors, including blue, and the blue part of the flame is the hottest part of the flame. So that kind of tells us a little something about the color blue right there. So, yeah, that's not right. All right, so the electromagnetic spectrum then is from radio waves that have long or large wavelengths and they have low energy, to gamma waves that have short or small wavelengths and have high energy. Long waves are less powerful and short waves are more powerful. So radio waves are very long waves that do not have a lot of power, a lot of energy to them. And gamma rays are very short and have very high energy to them. So Which waves are more powerful, radio waves or gamma rays? Let's see if you were paying attention here. If you said gamma rays, you were right. Okay, here's a little bit harder one. How about ultraviolet or infrared? So ultraviolet's over here, infrared is over here. Which one is more powerful? Which one has more energy? And if you said ultraviolet, you are the winner. So which color is more powerful or has more energy? Red over here on this end of the rainbow, or violet? Now, it's important to understand that violet means blue, as in roses are red, violets are blue, that kind of violet. Well, violet is on the higher energy side with shorter wavelengths, so violet or blue has higher energy. Now, take a look at this. We talked about red being on one side and violet being on the other side, and notice that right next to red, so here's red in the rainbow, right next to red, right there, is infrared. And we can't see infrared, we can't see it with our eyes, but it's actually kind of there at that end of the rainbow. And right next to violet, which is kind of right around here, we have ultraviolet over here. And again, we can't see ultraviolet, but it actually is there. It is a type of radiation that's there, but we just can't see it with our eyes. Our eyes kind of, it's like tuning into a radio. We can only see from here to here, but there is actually more stuff out here, just like when you tune into a radio station, you're hearing one radio station, but there's other radio stations are still out there, you're just not tuned into them. Well, our eyeballs cannot tune in to the part of the electromagnetic spectrum that's over here in this area, so that's ultraviolet, but we can't see that. And over here, right next to red, is infrared, and again, it's there, but we can't see it. So this gives you a sense, this image here gives you a sense of how big these waves are that we're talking about. So when you get to the point of radio waves, our biggest waves, they're about the size of, think wavelengths the size of a mountain or a skyscraper or a football field or something like that. These are really long waves, hundreds of feet in length. When we get down to the gamma ray end of the spectrum, we have things that are smaller than an atom, so really tiny here, very small. And in the middle, you can kind of see the idea, like infrared is probably about the size of your fingernail or something like that. Once we get into light, we're getting into the size of a pinhead or maybe the size of a bacteria, so down to kind of the microscopic size there that would be hard to see that size with your eyes. So all of these waves are waves that travel, and these are all, you may have heard of the idea of going at the speed of light. Well, this is kind of an interesting idea. Now, notice that light is just part of this electromagnetic spectrum that we're talking about here. So it would be better to say the speed of electromagnetic waves, but that's a lot of syllables. So we just kind of say the speed of light, but they all travel at the same speed. And the interesting thing about that is, well, that speed is really fast, 300,000 kilometers per second, which is equivalent to 186,000 miles per second. Notice this is not miles per hour here, this is miles per second. This is a ridiculously fast speed. But saying that it's fast doesn't quite get all of it in there. This is actually the fastest possible speed that anything in the universe can travel. And when I say that, I don't mean that this is the fastest speed we've ever seen, that it's the fastest speed that we can go at. This is actually the fastest possible speed that you can go at in the universe. Things cannot, by the laws of the universe, cannot go any faster than this. It is not possible, at least as far as we know right now, and we're pretty sure about that. Here's an interesting way of thinking about that. The circumference of the Earth, if you were to sort of drive all the way around the Earth at the equator, you would have to go about 40,000 kilometers. So how long would it take light to go around? Well, light could go around 10 times in 1 second, travel around the entire Earth 10 times in 1 second. That is pretty darn fast. All right, so these are called electromagnetic waves, and so they have sort of an electric part to them and sort of a magnetic part to them, as I talked about in the beginning. And you can kind of see the electric field going up and down here, and you can see the magnetic field going kind of to the side here, okay, horizontally. So we're going to try to draw this. This is going to really take your best drawing skills here. So, all right, you have a line in your notes that looks like this, and I want you to start off by drawing a wave like that. Okay, start on the left side, make it intersect with the line right about there, come back up, and so we want two complete waves to stretch out across this line. All right, here's the hard part. We got to make these guys kind of look horizontal here. So what you're going to do is start off at the end of the line again, but you're going to start going a bit to the left here. See how it goes to the left? And then you're going to curve it around and bring it back so it intersects with the same spot that the other line intersected with that straight line. Then you're going to continue on through, and you're going to go over to the right here, over to the right. Kind of go through there and come back to where this intersects. And then you're going to just do one more of those. Same thing again. Over to the left, bring it back around, intersect in the same spot, and then bring it over to the right and back a little bit. And then draw some of these vertical and horizontal lines in there. And one more thing, draw that. We have the electric field going vertically and the magnetic field going horizontally. And then we have the actual direction that the wave is traveling. All right, so when electromagnetic radiation, like light or radio waves or microwaves or whatever, when it hits something, it can do different things. And you're familiar with this. You understand that sometimes light bounces off of something, like when you're looking in a mirror, or sometimes light can kind of go through something, like when you're looking through a window. So this is what we're talking about here. You may have even experienced light being bent when it goes through water, like if you look at your legs when you're standing in a pool, or you look at a straw that's in a glass of water. So light can kind of do all these things. Electromagnetic waves can do all these things when they bump into something. All right, so first of all, they can be absorbed. This is like when you feel the heat from the sun, that's absorbing into your skin. They can be reflected. That means to bounce off like a mirror. They can be scattered, and there's two types of scattering that can happen: diffraction and refraction. I know these words kind of sound familiar, but you're going to have to get used to that. So diffraction we talked about in sound, and this was the idea that sound kind of bends around corners. And then we have refraction, and refraction has to do when light or other electromagnetic waves go through different mediums. So going from air to water, for example, or going from air to glass, something like that. So it's changing from one substance or one medium to another medium, and it gets bent in that way. Or they can be transmitted, and transmitted means they just go through it, like clear glass, like light going through clear glass, like a window. All right, so in your notes, and I'll check this in class, I want you to see if you can figure these guys out, see if you were paying attention. I want you to draw a line from the word to the correct picture. I'll help you out, I'll get you started. So reflected, that should be a pretty easy one. That goes to the little mirror ball here. All right, so let's talk about each type of wave a little bit and what they are used for. All right, so radio waves. These are the longest waves in the spectrum. They're the size of a football field or so, and they're really not very powerful waves. So here's a question. What do the numbers on your radio dial mean? So you guys probably all have your favorite radio station, and it has some sort of numbers, right? And then it says FM or possibly AM. So, well, okay, let's take a look. So we have this 96.15 here. Well, there's a hint for you as far as what that means. You should know what that symbol means. That's Hz, that stands for hertz. And hertz is a measurement of what? Hertz is a measurement of frequency. So that's what the numbers mean on there. Now, what does AM and FM stand for? Well, let's take a look at this. First of all, I'll give you a little hint here. The M, that stands for modulation, and modulation means to change something. So here's a question for you. On this top, on the AM wave here, what is changing? What are they changing? Well, it looks to me like they are changing the wave in this direction. They're making it kind of bigger and smaller that way. So what wave property is that? What do we call that? Well, we call that amplitude, right? So that one is amplitude modulation. In other words, they're changing the amplitude of the signal in order to create the signals that you hear on your radio. Now let's take a look at the FM one. So the FM one here, we can see that it looks like they're changing the wave in this direction. It's getting kind of squished and stretched out that way. So what do we know about that? Well, first thing that comes to mind might be wavelength. Hopefully that's the first thing that comes to mind, but we need a word that starts with F here. So what is another wave property that we know is connected to wavelength? Well, that is frequency. So FM is frequency modulation. That's what those two things mean. Tell your parents about that. So radio waves have a whole bunch of different uses. We use them for satellite signals. We use them for TVs and phones, obviously FM and AM radio and things like that. So we use these for a whole bunch of different things. This is something that you've probably heard of before. Now, you might not recognize that word radio direction and ranging, but that actually gets shortened to something, and you might know what that is, and that's called radar. So the ray in radar actually stands for radio because they use radio to bounce the signal off of things. And this might sound familiar because this is very much like sonar or echolocation where they were bouncing sound waves off of things, but in this case it's not sound waves, it's radio waves. Looks a little something like that. You may have seen jets like this. This is a stealth fighter jet, and you might wonder why they are stealth. Well, the idea of stealth means that they can't be tracked on radar. They can't really see them on radar. And you might think that that's some high-tech jamming device or maybe that some sort of materials that they use, but it's actually much more simple than that. The reason why these don't show up on radar is because of their shape, because a radar signal, radio wave comes in and hits it, and if it was shaped a different way, then the signal bounces straight back and they can read that signal. But with the stealth fighters, the shape of them makes it so that any waves coming in kind of bounce off of it at a different angle and go in a different direction and don't come back to their source, so they can never see those signals bouncing back. So the only thing that makes these guys stealth is the shape of them. All right, next up is microwaves. These are waves with wavelengths ranging from 1 meter down to 1 millimeter, and you know what those are. And think about the size of a microwave oven, right? From here to here, that is somewhere between 1 millimeter and 1 meter, right? And there's a reason for that. It's because the microwaves they use actually kind of fit into this box here, kind of like that. Microwaves are used for microwave ovens, obviously, to heat up your food, but they are also used for cell phones. A lot of cell phone signals are sent by microwaves. Next up is infrared radiation, wavelengths between microwaves and visible light. This is usually what we feel when we are feeling heat from a fire, or the infrared radiation is about the size of a pinhead. And we can use this for Doppler radar to find out where clouds are by bouncing off infrared rays off of them. We can use this for night vision in the military. There are a lot of animals, a lot of reptiles that are able to see in infrared, which makes warm bodies glow at night. We can use this to kind of see where houses are losing heat. and they're used to keep your food warm. Those are the heat lamps at McDonald's or the buffet and things like that keep your food warm. That uses infrared. Next up is light, all the colors of the rainbow, and something that we have figured out that actually a very famous scientist named Isaac Newton figured out by doing some experiments with sunlight and prisms. He figured out that white light is made up of a mixture of all the colors of the rainbow. And so those colors are red, orange, yellow, green, blue, and violet. So those are our Roy G. Biv colors, and you can stick an indigo in the middle there if you want to make that BIV nice and solid there. So this is what visible light consists of, Roy G. Biv. Please fill that in so you know the order: red, orange, yellow, green, blue, and violet. So which colors have the highest energy? Do you remember? Well, it's the guys with the short waves over here, right? Short waves have higher energy. So that means blue and violet, those guys are really the more high power side of things. It's worth taking a moment to talk about how we see color. So basically, we'll talk a lot more about this later, but basically, this is a green leaf. And so when sunlight hits it, which is more or less white light, really that's a mixture of all the colors together. And so what happens is most of those colors get absorbed except green, because remember, you are seeing green, which means the green must reach your eyeball and hit you in the eyeball. And so the green bounces off, it's reflected, and the rest of the colors are absorbed. And so we only see the green. Now, once it gets to your eyeball, you have these things in the back of your eye back here that look like this. And some of them are kind of shaped like that, like a cone shape, and some of them are more straight and shaped like a rod shape. And you can actually see real ones right here through a microscope. Now, basically we have the rod-shaped ones, which are called rods. Those ones are there to detect the amount of light that's coming in, and a lot of times they're used in very low light situations, and they don't see color. And this is why you tend to see things in black and white when it's really dark. But we also have 3 different types of cones. Each one kind of detects part of the visible spectrum of light, from short waves to middle waves to long waves. And so basically when things hit those cones, when those different wavelengths hit those cones, they activate that cone, and that sends a little electrical signal. And if you have a wave that's kind of in between 2 cones, in between the wavelengths, well, it will activate this guy a little bit, and it'll activate this guy a little bit, and your brain will get a signal from both and understand that that wave must have been somewhere in between. So that's really how we see all of the other types of colors, other than red, green, and blue. Well, this is a colorblind test. So if some of your red, green, or blue cones are not working correctly, you might have a tough time seeing the numbers in here. And for everybody that's not colorblind, well, you guys can probably see these numbers, but just to show you what it might look like to a colorblind person, that's what it would look like to them probably. All right, next up is ultraviolet. Ultraviolet has shorter wavelengths than visible light and is more powerful than visible light. This is actually an ultraviolet view of the sun. This is the ultraviolet light that it gives off. And you guys know that it gives off ultraviolet radiation because you have to put on UV protectant when you go outside, sunscreen, right? And the UV stands for ultraviolet. There are many different insects out there, insects that rely on flowers for their food, so insects like bees and butterflies that can actually see in ultraviolet because flowers tend to reflect a lot of that ultraviolet light coming from the sun. So to the bees, the flowers look like they're glowing. All right, next up is X-rays. X-rays have smaller wavelengths and higher energy. We're really getting into sort of the dangerous part here. You guys understand that ultraviolet can be a little bit dangerous, right? Because it's kind of powerful. So now we're getting into the more dangerous stuff. This is getting into more high energy here. So we use this for X-rays, basically because the ultraviolet rays, or the X-rays, sorry, will go right through skin and muscle and stuff like that, but it bounces off of bone, and so we can see that reflection. You may have been to the dentist before, and when they x-ray your teeth, they make you wear one of these vest things here, and that vest has lead in it, and lead prevents the x-rays from going through, and so that's just a little bit of extra safety for you. Now, why are these dangerous? Well, the reason is because they mess with your DNA. This is a DNA molecule here, and basically they can kind of destroy your DNA. And when that happens, the DNA becomes kind of, you could think of it as being defective at that point. And defective DNA, what it does is basically causes tumors. It multiplies and creates these defective cells that are not good for you. And that's basically at least one way that cancer can be created. All right, last but not least is gamma rays. These are the highest energy, shortest wavelength waves. These are emitted during nuclear reactions mainly. So we get these coming from large bursts from stars and things like that, and we also get it from nuclear explosions. These have a very, very small wavelength. That is the number right there, 0.0000000000001 meters. Very, very small. So the picture on the right there is basically a gamma ray burst from a dying star. And on the right, we see a nuclear explosion. Both are sources of gamma rays. An interesting thing about gamma rays is, as we talked about, these very powerful rays can cause cancer, but we can actually use them to kill cancer cells as well. So as long as they are very targeted, they can be used to kill tumors and cure people of cancer, even though they can also cause cancer as well. And last but not least, they are the rays that created the Incredible Hulk. All right, so there we have it, the electromagnetic spectrum. We'll be talking about that a lot in class this week. So these are waves of energy radiation. They are organized basically by their wavelength. We have long waves on one end, and those have low energy, and we have short waves on the other end, and those have high energy. They travel at the fastest possible speed that anything can travel in the universe. Radiation, when it hits something, can be absorbed, reflected, scattered, or transmitted. We'll talk about all those things in class. Types of electromagnetic radiation include radio waves, microwaves, infrared, visible light, X-rays, and gamma rays. And you should have at least a basic idea of what those different things are used for and know a little bit about them. And that's about it. I'll see you in class.